Hello, everybody. And as usually, I have a pleasure to invite our president, Klaus Mainzer, to say a few introductory words. So, Klaus, please.
Yeah, thank you, Dušan. And it's amazing this evening. I think we will consider an evergreen during our series Arts Meet Science, because that topic was so often discussed. The general idea that behind music and compositions, there are mathematical structures. And that will be discussed in the first paper. It is on complexity and fractal patterns, and we discussed it for several times. It's also one of my research fields, and it's a very old idea going back to the old Greeks and Plato and Pythagoras. You know that the belief that the universe is ordered by certain universal proportions. In arithmetics, it can be described by the proportion of numbers, or in geometry by the proportions of geometric figures, or in the antique astronomy by the proportion of spheres, and in music by the proportion of notes. And that was later on continued in Renaissance and in the Baroque time. So in any way, in the background of music, there are universal structures. This belief. And nowadays, in modern mathematics, that is described, and the first speaker will highlight that, by mathematical transformations, and that leads to more and more complex structures, and that will be in the center. There are more and more structures with increasing complexity. The structures can be very simple, for example, symmetric and in balance, equilibrium. And then the more complex structure is periodic. Development, rhythms, and canon, and something like that. Quasi-periodic means that even very complex structures, but are repeated, and then in the end, very complex chaotic structures, fractal structures. Fractality is a special kind of chaos mathematically, and you all know that. For example, the Russian dolls, which are inserted with smaller shapes, but the shape remains the same in infinitum, in infinity. And or in nature, fractal geometry, the fractal structures of plants, of fibers, or ferns, or trees, things like that. And that had also relation to that is geometrical, structural complexity. It has connection to computational complexity nowadays, because it needs more and more time and power to compute this more and more structures to simulate them. And as far as I understood the paper of the author, he will intend to apply these degrees of complexity now to music. How can we identify more and more complex structures and measure it in music? Now, and the second paper, very nice, because it's a practical view of a practitioner, of a composer. What does that mean? Composition cycles. Cycle that is periodic. You remember what I mentioned before. Certain degree of complexity in a canon, for example, the evolution of structures in composition. And so it leads to the special style. I think that's also a point of the second speaker, a certain stylistic style of the compositions. And so in the end, I think it's wonderful. Arrange the general structural view in the first talk, and then the application for composition. And I'm again very eager to learn more about that. also in relation with my own research interests. Thank you for your attention, and I'm convinced we will have a nice conversation. Thank you.
Thank you, Klaus, very much. And now I have a pleasure to introduce Professor Andrezej Herczynski, who is a research professor now at the Department of Physics at Boston College. First, he was educated at the University of Warsaw and in mathematics, and then at Lehigh, I hope I pronounced it correctly, University, where he made PhD in physics. And his research has been quite diverse and complex, from fluid dynamics and applied mathematics, linear waves in complex environments, and colloquium instability of viscous liquids. And for nearly 2 decades, he's also been interested in connections between natural sciences in general and visual arts, and recently also in mathematical aspects of music. About almost 10 years ago, he was the principal organizer of the program of growth, form, and self-organization at Isaac Newton Institute in Cambridge. And this included also an exhibition Form in Art, Art in Form. For the last 5 years, he's been organizing a series of workshops funded by NSF, exploring the intersection of science and art. So he was, from his papers, you can see that he was interested in fractal partners in music, fractal contours, order, chaos, and art, colloquium instability in the kitchen, structural complexity in music, and viscous coiling on a spinning surface. So you see, this is really included in every aspect of our life and nature. And Andrew, please, the podium is yours. I'm looking forward to your presentation.
Andrew.
Yeah. Okay, I hope you see my first slide. Thank you so much for these lovely 2 introductions, Klaus and Dušan. And I'm happy to be here. This is my second talk for this August audience. And this time I'll talk about music, as you've just heard. I want to first mention my co-author, which is John McDonough, with whom we wrote 3 papers by now and working on the 2 more. And I also want to acknowledge a number of musicians who provided critical assessment of various stages of our papers, gave us ideas and so on, as you can see in this list. Of course, all the shortcomings are my own. Now listen, we are taking a very different approach from what's usually done in literature on these topics in music. I like to say that our approach is perpendicular to what has been done before. So I want to start by motivating it. And the most common approaches in the literature are either statistical or based on networks, and sometimes both of these things simultaneously. So here's some caveats about these approaches, particularly in reference to complexity. So complexity measures are most often based on Shannon information entropy and other forms of entropies.
Andrew, we do not see you. We see you. You intend to show us something.
Yeah, I did.
Please.
I had this problem before. I don't know what's going on. Let me try it again. Are you seeing the lens?
Wonderful, it's perfect.
All right, and do you see my slide?
Yeah, we see now the beginning. some statistical network approaches.
Okay, so I was just, okay. Maybe I should,
now it's music also.
Yeah, music.
Wonderful.
Okay.
Yeah.
Okay, I'm a little discombobulated here. Okay, so now you can see the first slide, which, and I was just talking about my co-author here and musicians who helped. Can you see that?
Yeah, we see. We see now.
Okay, good. So now I want to talk about some caveats about standard approaches, which, as I just said, are usually using statistical tools and network approaches and similar things, and they're often based on entropy. But there's problems with this because complexity usually achieves its maximum value at intermediate entropy. And for random set of nodes, entropy is infinite, but complexity is small. You may even say that in some sense, a completely random set of nodes poses the simplest kind of composition that anybody can do. Second, statistical parameters in network analysis are global properties of entire compositions. Whereas the character of music changes in time. So it should really be analyzed locally, not globally. Some people analyze the whole Fifth Symphony of Beethoven from the beginning to the end. But there are a lot of different things happening, even within one movement, even within a subsection of one movement. And finally, statistical parameters, by their very nature, depend on averages. There are almost always, with some exceptions, insensitive to order of notes. But music depends on precise sequence of notes and cannot be understood in an average sense. So what we propose to do is to analyze music based on motifs or themes and include both the pitches of notes and duration of notes and rest as written down in this course. And we omit all the properties of the performance, such as loudness, what instrument was used, and so on. So let me start with tonal complexity. We start by using the properties of equal temperament scales, which are defined as shown here, basically by ratio of note frequencies, not by differences, but by ratios, so that when the ratio is 2, which corresponds to 12 semitones, that is 1 octave. It's important that this is, in fact, how scale is defined, because this corresponds to the logarithmic hearing that we humans have. And not only we, all mammals, and I believe many other animals as well. I don't know how snakes hear. Maybe they don't have logarithmic hearing, but most animals do. So we assign a complexity to a theme, tonal complexity, to a theme based on, composed of n notes, capital N, as shown here, that is to say in intervals measured in logarithms. Now, I don't have time to fully explain here, but the constant chi sub t 0 is just a normalizing constant, which assures that if the motif is repeated, the complexity does not increase. And let me also say that this can be simplified and written in this form, where you explicitly have a sum over differences in these indexes indicating semitone distance from some reference frequencies as defined at the top of this slide. Okay, now let me mention some of the desirable properties that this has. First of all, it is local. It depends on the order of notes, as it should, and on pitch intervals. In logarithms, the larger the pitch intervals, the larger the chi sub t. The larger the number of non-zero intervals, the larger the chi sub t. If all the notes have the same pitch, chi sub t is 0, as you would expect. Tonal complexity is 0. And within 1 octave, this tonal complexity is between 0 and 1, which is a desired property. Here are some examples. These are synthetic examples. And below these 4-note examples, I show the tonal complexity. I want to bring your attention to these 2 examples with the red arrows that have the same tonal complexity, but are different. How different are they? They differ by an inversion and transposition. And more generally, transpositions, inversions, retrogrades do not change chi sub t, which is what you would expect. By the way, entropic definitions do not have these properties. Okay, I want to show you how our measure, this which I'm showing here again, compares with experimental work where people were asked to judge complexity of music. So in this graph, the blue line is based on votes from a number of students, actually a fairly small group of students who rated complexity of various computer-generated examples. And in red squares is our measure. You see it basically follows the same trend and agrees pretty closely. Just to explain what's going on here, we're plotting things as a function of beta. Beta is an exponent in the power spectra, as shown here on the right. And the important thing to note here is that as beta increases, the average distance in pitch between notes decreases. So if the average distance in pitches decreases, then our measure, shown here at the top, will also decrease. And this is why our red squares here, our measure decreases, but it agrees actually surprisingly well with this experimental study. By the way, there's very few such studies that one can compare with. This is one of the few that we could find. Okay, so much about that. Now about rhythmic complexity. So now we need to have a measure of for notes durations and rest duration. And here by kappa, I denote the duration of a note. It's in music defined as a power of 1/2. And this is basically defined by the exponent here, which we call m, duration index. And we do it in such a way that, as you can see here, whole note has an index 1, half note has an index 2, quarter note index 3, and so on. All right? So now we define rhythmic complexity in a way similar to tonal complexity, also by logarithms. And here's a form. It's very similar to what you have just seen, with one exception, that the normalization constant chi sub rho needs to be chosen a little differently. First of all, you can simplify this to a similar form that you have seen before. And now I just want to say that we define the normalization constant in such a way that based on this inequality, which I'm just showing here, which is the sum in the definition above, we define the normalizing constant as twice the sum of all these indexes m. And what this ensures is that this complexity, rhythmic complexity, is not more than 1. And the properties are very similar to what you've seen before, so I'm not going to spend time elaborating on them. The third thing is if you sum these two things, we call this structural complexity. So structural complexity is the sum of these two complexities corresponding to two main characteristics of music, its tonal and rhythmic content. So here is a synthetic example, 6 of them actually. And here are the various values we've calculated. By the way, the calculation is very easy. After a while, you get to see how easy it is to do. I want to emphasize 2 examples, namely B and D, which you will see are completely different above. However, they have the same total or structural complexity, 5/12. However, the first of these, B, has tonal complexity 1/6 and rhythmic complexity 1/4, and the other just the other way around. So you can see that this can happen. All right. So, and you can also see that these tonal complexities probably correspond roughly to what you would expect, with the last one being the most complex, both rhythmically and tonally. Now, here are the real examples, music examples. I'm going to show you 6 of them, but just show and play 2. So here's the famous theme from Stravinsky, from The Rite of Spring, that has all identical notes. This is the Augurs of Spring theme. It has our measures 0, tonal and rhythmic complexity. I want to immediately say this does not mean that this is not an interesting piece of music, quite to the contrary, but it's, in fact, some of its interest arises from the very sharp entry of each of these identical notes with these accents, which I show. And the accents, which are under the stuff, you will see are in some irregular fashion added to it. Here is the first example where at least one of those parameters is non-zero. This is a famous piano etude, Un Sospiro, or a sigh in English, from Liszt. And here, all the notes and rest are of the same duration, but the notes are of different pitches. So there is a non-zero tonal complexity and 0 rhythmic complexity. Here is the opposite example. This is an aria from Rossini, which has all the notes of the same pitch, so the tonal complexity is 0, but the rhythm varies. By the way, Rossini composed it because he had, for the first performance of this opera, a soprano who he thought couldn't sing any other note except this one, which is B flat. And so he composed for her an aria that's his only B flat notes. And 2 more examples, Copland and Beethoven, where both of these indices are non-zero. I can't play all of these, but I'll play a little bit of these 2 so you can see how this works. So here is the list. I want to say, in addition to the theme that I've shown you, there is also accompanying arpeggios, which we do not analyze. You can see these arpeggios on the screen. However, the theme will appear in the 3rd line above this. So here's this piece, so you can hear the theme with the notes of equal and rest of equal duration, but the tones changing. Can you hear?
Yes, we can.
You see that the arpeggios are just an accompaniment. The melody is in the top line, And an interesting part of this is that the top line is played both by the left and right hand as is convenient. Here is the Rossini that I've advertised. Here, all the notes are of the same pitch. Tonal complexity is 0. Rhythmic complexity is 0.2. It's just the opposite example. So just one note from the singer, and everything else is done with the orchestral accompaniment. Now I want to move on to fractal patterns. So first, as a reminder, 2 classic visual fractals. The first one was Cantor set. It wasn't, Cantor didn't know anything about fractals. That term was coined much, much later. And here is, let's wait till it restarts. You start with the interval, you take 1/3 out. From the remaining 2 parts, you take 1/3 out, and so on. And the fractal dimension here is defined by the log number of copies at each stage divided by log inverse scale. The scale here is 1/3, inverse I called S is 3. So the fractal dimension is log 2 over log 3, 0.63. That tells you that this fractal is about halfway in between line and a point. Here is another famous one, Koch curve, from a little later. And let's just wait to go. And it's composed out of making these little hats. So first hat, and on each part, another little hat, and so on ad infinitum. And here at each stage, there's 4 copies of intervals. And the scale is the same as before. And you take log 4 over 3, it's 1.26, which tells you that this creature is closer to line than to a plane. All right. So we want to mimic it somehow in music. So here are the guiding analogies between visual and musical fractal patterns. First of all, images are static. Music changes in time. So all the voices or lines of music need to be considered at each instant of time. Visual fractals depend on scaling regularities in space. Musical fractals must depend on scaling regularities in time. Self-similarity, key feature of fractals, in an image implies the same pattern at various spatial scales. Self-similarity in music must imply the same motif simultaneously at varied tempos, i.e. via augmentations or diminutions. Okay, so therefore, really what you have is a definition of a prolation canon. That's a composition where you have several lines of music simultaneously playing the same sets of notes but at different tempo. It's also called sometimes mensuration canon. Okay, so a little more about these prolation canons. In regular canon, which you all know very well, a melody overlaps with different parts of itself due to a time shift or delay in the entry of separate voices. But this shift remains constant. In a prolation canon, a melody overlaps with different and all the time new parts of itself because each line unfolds at different speed. So it's a serious complication. We don't know for sure, but probably this technique was invented by Johannes Ciconia, a very important figure in ars subtilor, or subtle art in music. It was developed in many compositions by famous composer Johannes Ockeghem, and then perfected by his student Josquin de Prez, who was a mathematician and a musician. And the first two known examples are by Cicogna from around 1390 and from Ockeghem about mid-15th century. So this goes really back, as Klaus was saying. This is not a new thing, but it has continued to our own times. In fact, correlation canons are quite popular these days. Okay, so now I want to define fractal dimensions. I'm going to go pretty fast through this. Sorry, a little mathematics. But suppose for a moment you have a correlation canon with just two voices, right? Two lines sung or played simultaneously. And suppose that the motif that defines each of the voice in one line lasts a time t1 and in another t2. And the number of repeats in each line is R1 and R2 correspondingly. Then, to extend the analogy with visual fractals, the number n, which is the number of copies, must be a relative number of repeats in line 2 relative to line 1. And the scale must be the timing in line 2 relative to timing in line 1, right? Everything is relative. And that basically means that you take a ratio of the logs of R2 over R1 and then T1 over 2. Notice the different order here. For little n voices, we just generalize this. So we have a sum. You have to divide it by little n, the number of voices, to avoid the repeats here. And we have log of the relative number of copies or repeats in line I relative to line J, and then the scale is of line A relative to line J, and then the scaling factor S must be 1 over this. All right, so that's how D0, which we call temporal fractal dimension, is defined. Now, in order to accommodate also the tonal and rhythmic complexities that I just talked about, because this number can be defined no matter how complex or not complex the piece of music is, but the fractal dimension should reflect this. We introduce tonal fractal dimension and rhythmic fractal dimension, and the net fractal dimension is the sum of these three things. Okay. Now the chi, whether it is this complexity, whether it's for tonal or rhythmic, can be treated as a weight modifying the scale epsilon. And there's reason to do this, which I don't have time to go. This is the simplest thing you can do. And if you do this, then you can define the tonal fractal dimension as I've shown you here, where you can see in the denominator chi sub t, the tonal complexity appears, and very similar for the rhythmic complexities. And this has all the properties that you want it to have. I'm not going to dwell on this, but for example, if there's no scaling whatsoever, that means D0, the temporal fractal dimension is 0, then the other two are 0. If the tonal complexity is 0, then the tonal fractal dimension is 0, etc. Okay, so now I want to give you 3 examples. This first example is from Josquin de Prez, a master of this form, as I've just said before. And he's done this many times, but this is the most famous example of all his examples. It's the second Agnus Dei that he wrote towards the end of 15th century from his very, very famous mass, Missa l'Homme Armé super voces musicales. And it's based on a very simple theme of 4 notes, 3 identical notes, and then one just raised by 2 semitones and extended in duration by a half. And of course, I wrote this here in the modern notations. And if you take the middle line to be rectus, to be at speed 1, so to say, then the top line is 3 times as fast and the bottom line is twice as fast. So first, I just want to show you what this sounds like on a synthesizer. And here, this is what we call Euclidean fractal. So D0, the temporal dimension, is 2. The other 2 are, the rhythmic is nearly 0, as you can see there. And dt is quite large, is about more than half. So that the total fractal dimension is about 2.6. Here is this the same piece performed by a choir. And this is what Josquin actually wrote. It's just one line of music. Everybody sings from this line of music. And you're going to see 2 lines, each moving across this score with the appropriate speed. So here it is. So you can see this is really complex, and yet it sounds perfect. Here's a second example of my 3. You all know about Goldberg variations, but at the end of his own copy of Goldberg variation, Bach wrote just one line of music, which he called the canon. It's actually his 14th canon. Here's what it looks like. It's based on the 8-note Goldberg theme shown in here in this frame. And here the speeds are, the soprano is rectus, and the other lines are at quarter, half, and 1/8 of the speed. Here's what it sounds in a synthetic way. This is a slightly more complex piece of music. D0 is 2.6. Tonal dimension is a little over 1. The rhythmic dimension is not 0, but very close. As you can see over there, there are all 16 notes and 1/8. So the total dimension is about 3.7. And here's what this thing really sounds like, performed on 2 harpsichords. This is what Bach wrote, just that. And now modern notation. And this theme is inverted, inverted again, adjusted a little bit. Here are the speeds of the performance. the idea. And my last example is from Shostakovich, is the most complex example. This is an allegretto from the first movement of his last symphony, number 15, which he composed in 71, shortly before dying. And he's a very simplified view of this. Of course, there's the whole orchestra. The theme is an 8-note theme shown in here. Here, the note durations are exactly the same everywhere. And the top line is the rectus, and the other two are 3/4 and 5/8. Very odd ratios of speeds. And if you compute things, first of all, let's hear it. I'll play it one more time. It's a very disquieting theme. On purpose, of course. D0 is very large. It's 8.5. DT about 1.4. And the total dimension is 10. So it's a very complex piece of music, as maybe you could gather from this. And now I'm going to really play this so you can see why it's composed in this way. Again, the repeat of the theme. Very high tension. I think enough of this, but you're getting a sense what role it played in the composition. My time is, I think, almost over, so I'm just going to mention that there's a lot of details that I had to skip over. They are in these two papers we published in Chaos, Solitons, and Fractals 2 years ago, and last year in Advances in Complex Systems. And I want to complete this. Oh, and we were working on a sequel to this with 3 concluding remarks. First of all, mathematics and music are really bound together. This is a statement of Helmholtz, a physicist. From the construction of musical scales to transpositions, augmentations, diminutions, inversions, retrogrades, and other mathematical transpositions. Scaling regularities in music, especially in prolation canons, require the highest level of mathematical and musical dexterity from composers, and also a heightened attention from listeners. And structural complexities and fractal patterns in music convey a perfection of form, a sense of inevitability in the musical development, and a hidden but rewarding order. And as Josquin said, the overriding principle was that of harmony and proportion. The music had to be a reflection of the balanced order of God's universe. Thank you very much.
Thank you very much, Andrew, for this fascinating presentation.
Thank you.
We shall have discussions after the second presentation. I'm very happy to invite Carmen Carneci. She is also my colleague in Romania. First studied in Bucharest, later in Freiburg, and she received also a DAD scholarship. She worked with great personalities like Pierre Boulez, Klaus Huber, Peter Oetrich, and many others. She was invited both as a conductor and a composer to important festivals of new music, and also as a guest conductor in Stuttgart, Kammer Theater, and the State Opera in Milano, Piccola Scala, in Bonn, Opera House. In Bonn, she also gave the world premiere of her own chamber opera, Giacometti. As a composer, she received awards in Mannheim, Rome, Köln, Bucharest, had a work selected and performed in the World New Music Days festivals in Luxembourg, Zagreb, Hong Kong, Tongyong, Beijing, Lisbon. She received a number of commissions, Heidelberg, Bonn, Donaueschingen, Zurich, and so on. In Bucharest, she is a guest professor at the National University of Music, artistic director of the International Week of New Music, and of the concert department of the George Dinescu National Museum. Since 2005, she has managed and conducted the Ensemble for Contemporary Music Devotio Moderna. Her works are published by Ricordi, Furore Verlag in Kassel, and Editura Musicale Bucharest. Carmen, thank you. You have the floor.
Thank you for the introduction. And I'll be quicker than I thought I have to be. The time is short. So slide one. My topics. So this is genesis of my composition cycles, and the main ideas are about the emergence of the material, the generative power of the original idea, and the attraction of creating variants for certain instrumental destination. The presence of cycles in the creation of contemporary composers would be a subject of larger musicological research. The cycle of 14 solo pieces called Sequenza by Luciano Berio certainly caught my attention, but I only went through a few of them. Pierre Boulez also composed variations on some earlier pieces, which again seemed to me to be an attitude with which I resonated since my master's studies at the Musikhochschule in Freiburg. Much later, I went through the biography and the impressive list of works of my compatriot Corneliu Dan Georgescu, in which I found the approach of cycles of works, which gave me a feeling of kinship. I could mention a series of names of composers who approached the cycle frame or pattern. Still, I come to my own pathway. Yes, this is the chronological list of my works from a first period of creation. I will run through it. This a solo piece for violin, and then Colinda, instrumental theater piece for trombones and percussion, then Soma dance for flute or flute and percussion, and Arterklang, Baumklang for string instruments, and a piece for voice, and 5 instruments on lyrics by Magda Krnec. Then in 1990 and 1992, without emphasizing their kinship through a subtitle, so I didn't entitle them Cycle, there are 2 pieces composed almost consecutively on lyrics by Annie Cohen, a very interesting poet, Que des âmes and Que des morts. These 2 form a first mini-cycle from the very beginning. Why? Through the text, from which I have taken 2 fragments. So the same poetic tone generated not only a cycle connection, but also a clear stylistic imprint. So this was a first moment in it was a first moment in my composing when I returned to an earlier work. Why? Because its generative idea was emerging again. This phenomenon repeated in my creation by virtue of an underground continuity of a type of expression, or a persuasive, even obsessive content, which needed to be expressed again in new dimensions and a new shape. The music composed in these ways generated several cycles that helped in designing my own stylistic identity, being also as a sign of more composing experience. The stylistic identity can be directed and constructed as a process, or reveals its frame and parameters at a given moment from accumulations of a number of works, even those finished at longer intervals of time. I will exemplify these ideas by briefly presenting the cycles Giacometti-Scenen, Omens, Origami, Solitary Psalms, Asterism, and Orpheide. Well, some of them. So long the time will be. So I come to a very important project of mine, composition project, Giacometti project. And here you can see the list of the chronologic history of this project, which starts with a piece for oboe and clarinet, Sommet de Morphine. The same piece will be put in other instrumental formulas with some very specific variants. I'd like you to listen to this Sommet de Morphine to the beginning, because it is very generative for the whole opera Giacometti. Thank you. Okay. The whole piece is wonderful, played by okay. Okay, posso continuare? Posso far best? Okay, excuse me. I can go on now. So this was wonderful, played in the concert in 2010 in Stockholm. This is the first piece which generated, in fact, the whole opera. And I would like to go also at another title from the same project. In this respect, this is the cycle of Giacometti-Scenen. And on this list you may see in red is twice it appears Giacometti as an opera with two versions, one in 1995 in Bonn and the second one in 2001 in Zurich. And all others between and after these red titles are die Szenen, also the scenes. Okay. Era okay, Frankenstein. Nu Palastas, nu știu ce. Lichtung. Okay, another piece, which is a scene, so a scene from the opera, is Lichtung. Am unul cu două poze de partitură pe slide. Okay, asta. Okay. Now you may see. So Lichtung 1 and Lichtung 2, two Szenen, Giacometti Szenen. So Lichtung 1 was also a very early piece in this project for solo piano, and I enlarged some time after the resonance space of the same music, sharing but also varying it, reshaping it for two pianos. And so this is Lichtung 2, Giacometti Szene. And I would like you to listen to maybe 1 minute from this. So my strategy here was to undo the tight polyphony of the solo piece, to enlarge and project this content into new registers and dynamic planes. And still it is the same music, but recomposed with a bolder sense of space. And this interested me in this cycle. Another piece which is interesting for this theme of cycles, also from the Giacometti Szenen. Dar întâi punem-l ăla de aici. Îmi punem slide-ul. Da. Cu două mai sus. Okay. Now one can see here in comparison Femme couchée qui rêve, Giacometti Szenen from 1999 for voice, clarinet, and percussion. And on the right hand, this is Qui rêve, Giacometti Szene for bass flute. And I would like to stress that this second piece, Qui rêve for bass flute, is, as the title shows, a truncation and variation of the flute part in Femme couchée qui rêve. And I like to do this as a rereading of it, of the first one, still remaining a version of the same root, which I wanted to construct to express nocturnal and dramatic from the mother piece, which remains the whole chamber opera. And a very short fragment from Kirev, played by nu asta. Okay, played by Ion Bogdan Ștefănescu. And here one can see the score too. Okay, motto on this slide. So this was a little bit from this Giacometti project and Giacometti and the cycle of Szenen. I'll go and present very quickly another cycle that was important for me, the Omens cycle. As a motto for the idea, generating idea, is Omen has the meaning of a prophetic sign that conveys to us a message engraved in nature and in the events of life that we must observe and then decipher. Carlos Castaneda often uses it in his books. And the Omens cycle is about sound landscapes designed by iridescent reflections of ever-changing streams of sound wave. And this cycle, I composed Capriccio for clarinet, and then Herb's Steps as an animated landscape for clarinet and orchestra, and then Omens Mnemosine for guitar quartet, which I would like to present to you also in sound. this is very short fragment from the beginning. I especially composed this for Quasi Fantasia, this guitar quartet. And what I think I need to say here is about the sound. There are sounds designed to have the power to recall impressions submerged in memory. So mnemosine is the word for memory. This being done through echoes of a free game like clay bells, regular pulses like a pendulum, measuring another time, or quasi-onomatopoetic signals suggesting an open frame, a place in nature that reminds you of yourself. In the same ideas, I composed Omens Akin for solo flute and flute orchestra, commissioned by Pierre Rivarto and Orchestre de Flûte Français. And I would like to offer the beginning of this concert. It's a concertant work. Another cycle with solo pieces is origami. And I would like to present very shortly one of the pieces in origami cycle, origami with blackbirds, and in which for flute, in which I assimilated the origami technique to the composition process. So I created three-dimensional figures from a sheet of paper through handcrafted folds. It's a metaphoric said. So the form of the piece is a free one and can be described as a string of 7 ample phrases of varying sizes, which enunciate a melodic content in continuous reinvention, similar to the song of a blackbird. And this is the variant played by Eric Drescher 2 years ago in Berlin Klangwerkstatt. Well, as a final word to this presentation, there are other 3 cycles in my composing: solitary psalms, asterism, and Orpheide. I don't have now time and space to present them, but maybe another time. And also in the paper, I hope I'm going to do for you.
Thank you very much, Carmen. Thank you for your music. And I would like now to invite our Vice President to say some words. Hello, Johannes.
Hello, here I am. Yes. Oh, thank you. Thank you. Amazing, both of the talks tonight. Amazing. I would like to comment on first by Andrezej. It was an illuminating presentation, which showed how musical thought has long anticipated ideas that we now associate with mathematics and complexity science. By moving to beyond global averages to a local motive-based analysis, I would say, Andrezej demonstrated how scientific tools can respect musical articulation rather than flatten it. What we hear today confirms that music is not only an object of aesthetic experience, but also a structured system capable of revealing deep principles of organization across scales. This contribution exemplifies the spirit of arts meets science, not by reducing art to numbers, but by allowing science to sharpen our perception to artistic form. Thank you for opening this rich interdisciplinary dialogue, Andrezej. For the Carmen, thank you, Carmen Carneci, for this deeply reflective representation, which offered a rare insight into composition as a long-term process of emergence rather than a sequence of isolated works. And the idea that a generative impulse returns, transforms, and insists on rearticulation resonates strongly with scientific notions of continuity, iteration, and self-organization. What became clear to me is that artistic identity is not simply designed, but gradually revealed through time and accumulation. In this sense, composition appears as a form of inquiry where intuition and structure evolve together. This perspective beautifully completes the arts meets science dialogue by showing how creation itself embodies principles we often associate with scientific thinking. By the way, you mentioned in one of your slides the Carlos Castaneda, which was used, the omen, was, as we know, highly influential, but on the other hand, controversial figure, whose literary success blurred lines between anthropology, fiction, and mysticism, making him a key, albeit debated, cultural icon. And the omen for Castaneda was just a sign, but often a visual phenomenon, like a dark spot or a feeling, as that appeared when perception shifted from ordinary reality. Also, hallucinogenic plants you mentioned, herbs and others in his early books. Reminds me Pythia, the priestess of god Apollo temple in Delphi, also Asclepius' methods of therapy with music and other unknown agents. Thank you.
Thank you.
Thank you very much. I would just have to mention that young Bogdan Ștefănescu, your wonderful flutist, is also with us.
Good evening.
Yeah, and I discovered, look, he's here. Great. Congratulations. I would like, so if you have to say something, but before I would like to invite Jeremias Schwarzer. He just made a sign. He would like to comment something.
Bravo.
Yes, I would like to ask something which just came into my mind because we have so many really great composers present here and musicians. And I was reminded very strongly now about some words which Armin Köhler was telling. He was the director of Donaueschinger Musiktage and died some years ago when he was giving a lecture about contemporary music. And he said, in his perception, and he knew a lot of contemporary music, there would be two main different ways of working as a contemporary composer, and I found that very interesting. And he said the one thing is that the music is telling a story or a drama, and then the perception of the listener is taken in, and you are part of something which is transformed, and you are transformed, and you are in the middle of something. But he said, especially in contemporary music, there's another thing he would observe as kind of working with music like an object, like something where your perception can go around things, where you can perceive, and when your perception can travel around the structures of the musical artwork. And he said this, for him in contemporary music, these two ways, of course there are many others, but are very much perceptible, that composers go either that or the other way. So either the drama or really looking for the structure and for the perception. And for me, it seems to be interesting that if you go for the architecture, for the structure, you come always to modal structures, so to scales or to something which you can extend or diminish. Or I find it very interesting that all the music now talked about, also Josquin and others, have so much to do with modes, more with modes than with the drama of harmony. So I think, could you rely a little bit on that, the composers who are here? If you go for architectural things, how do you choose the material, and why is it often so much a modal system you use then, or you come up with for this way of work?
E o întrebare asta?
Mm-hmm.
Is this a question to me?
Yeah.
Okay.
Also, of course.
Yes, there are pieces where I worked a lot for shaping the material, and I worked a lot with modes and with scales and with generating rhythm. But what in fact made me happy and was that all this preface of composing at a moment disappeared. It's like, I didn't want to be this transparent, but to have the expression and to have this drama. I am more interested in drama, but this structuring is very, very present in my music, but somewhere where it's not so very visible. Expressing, but not so very visible.
Thank you very much. Andrew, do you have also a comment on this aspect? And then I would like to invite Dušan to speak. And Andrezej?
I'm not sure I have a comment about this. I think there are a number of different ways of composing, and I think I detected both of those that were mentioned in Carmen's music. It's very striking, and it's. I'd be curious to to analyze it. It was particularly nice to see the score, and I think I understand this music better when I see the score. So it was very good to see the score and see these incredible jumps in pitches, which provided a lot of drama.
Thank you, Andrew. Dušan.
Yeah, I'm still glad that I have some battery left to be able to ask. First, I'd like to comment the first lecture. I enjoyed it because fractals we can see in nature. Let's say if you look from molecules to cells, organelles, and in animal, you see this structure repeating itself. So it's really interesting. And the other one, I'd like to ask a question. What do you think about your music and modern music in general? It was dramatic, but whenever I listen to modern music, I think I would like to have it combined with another art, let's say visuals, let's say pictures or sculptures or something else. So I always have a feeling that it needs some complementary art. It's the same with abstract paintings or sculptures. I also feel music when I see that. So what do you think? Is it good enough or not good enough? But do you think there's any added value if your music or maybe some other modern music would be combined with other forms of art?
As a general idea, contemporary music as music from every time should be sufficient to itself. But in the last time, so everything is so much developed, we need more information. So visual and information coming from other arts are very welcome by the contemporary composers. So I notice that in the festivals, this part of video of presenting our choreography or implicating lights and also arranging the scene, so arranging the space became more and more wanted and appreciated. And I noticed the public likes more the contemporary music, accepts this more difficult level of perception if it is presented with something else, like lights, videos, also, I don't know, everything which choreography. So I myself was happy to get versions by very young choreographers on my music, and I was so very surprised. So my answer is yes, we are in a time of all contemporary music is now going in the agora. So we say, the composers, we want a better, more interesting presentation. We agree that the other arts are our sisters. So please, let's enjoy together.
Okay, thank you very much. Thank you.
Thank you also. It's somebody who would like to say something? Myself, I can say that I was myself at the world premiere of Giacometti in Bonn when Carmen conducted her own work. And I understand very well what she said, that at the same time you need to understand and to create structure and also to discover the narrative, what she has to say. I have a question for Andrew. You use the notion of tonal complexity melodic complexity. What happens when you are, for example, make an analysis of the piece of Carmen, because it is not tonal. So do you need another notion when you say you need only melodic complexity, or this is my question, I'm curious.
Good question. I'm not sure. I was looking at the score carefully. There are parts of it that I wouldn't know how to treat using our methods, and parts of it that I would. We are also not, as I've alluded briefly, we're not quite ready to analyze chords and chordal music. So, in short, it's probably difficult to analyze the tonal content of at least the piece that I saw the score for. I'd have to think about it, but it's certainly a challenge to analyze it mathematically.
Thank you very much. It's a topic for the future of your research. It was so fascinating to see what you described. I'm happy to invite now Klaus Mainzer, our president.
Yeah, this evening actually I enjoy both talks very intensively, because it was so nicely arranged. First a theoretical approach, then the practical approach of a composer. Now I have two short questions. First to Andrew. As you know, in complexity research, roughly complexity degrees, we distinguish very simple equilibrium states, and then periodic, quasi-periodic, more complex repetitions, and then the chaotic structures with fractality. Now, there are different measurements for measuring this different complexity degrees, and there is power spectrum, there is fractality. Fractality is only one measurement of dimensionality, and there is the Kolmogorov-Sinai entropy, which is measuring the information loss in structures. So my question is to you, very concretely, for your task, analyzing musical structures, which kind of complexity measurement do you prefer? And for Carmen Maria, when I may say so, my question is also very practical. You are a composer, and so I'm wondering, what is your inspiration? Do you have some structural problems, and then you try to elaborate it in a musical way, or are you inspired by a certain feeling, perhaps? For example, Beethoven explains that he was walking in the forest of Vienna, and then he had a special feeling, and then he wrote his Pastorale. That's an extreme example in this case. Or is it more structural, analytical, abstract? How do you work to find these amazing and impressing melodies and rhythms? Perhaps Andrew, and then Carmen Maria.
Thank you. This very interesting question. Look, I don't have a preferred way. The fractal dimension is not really a measure of complexity. It's measure of structural regularity. Now, look, this is a topic that has been debated a lot, and most physicists attribute complexity according to entropy. However, I think in the 70s, Murray Gell-Mann, a Nobel Prize winning physicist, wrote a very famous paper called What is Complexity? And in it, he argued that entropy is not a good measure for complexity, that systems which are very well organized, so in music it would mean a series of identical notes, I have entropy 0, and systems that are completely random, whether it's in thermodynamics or in other contexts in physics or in music with random notes, have entropy infinite or very large, but are not very complex. And he argued that that complexity measure, however you define, should be such that the highest complexity corresponds to mid-range entropy. And very recently, there was a paper with the mathematical ideas behind it. I, of course, don't have time to summarize it here, but that's my main, that's what I believe in too. I believe that entropic measures are not appropriate for all the reasons I've mentioned. In some sense, both ends, completely identical notes and completely random, have a certain childish simplicity, right? Both can be composed by people who know nothing about music, but to be in the middle, it's tough. Kolmogorov measure, it's rarely used these days. It's interesting. It's very hard to implement in practice because it talks about the lengths of algorithms, and these days, different algorithms you can write at different lengths, and so it's not very practical. It's a little unsatisfactory, maybe answer, but it's the best I can do.
Okay, thank you. And now,
Well, yes,
I'm very eager to hear more about this because it's an approach to modern music and maybe different to former times of composers.
So my answer to you is that I appreciate inspiration. So I can just have a very good, dream, let's say, and I go and note my lines, and I design, I write notes and put there, and it waits for me. I have my analytic phase of work, and what I mostly enjoy, love, is to modulate a certain material. So a raw material which is given to me only by mathematics or by, I don't know, raw rhythmical treatments, and so makes me not happy. So I want to be happy through this work. So I like to modulate. And as you could see in the score for bass flute, there's a lot of fresh things which come over measures and weighted rhythms. So I like this. I appreciate this. I want to do this. But of course, because I am also conducting, and I've conducted a lot of contemporary music, a lot of scores, different musics. So I have many sources. I can imagine immediately a certain drama, as someone said that. And yes, I like soundscapes, and I know to build them. So it's also a sort of experience in the good sense of the word. And also I like dramatic. And in this opera, I put dramatic into a very, very, technical and rational treatment of all the materials. This Giacometti opera, chamber opera, from which afterwards I extracted some scenen, some scenes which I liked. So I really want me, first of all, to like the music I'm creating.
Thank you, Carmen. Thank you very much. Now I would like to invite Mihaela Mozganian, as a composer, to comment. Mihaela?
Thank you very much for the presentations. Both of them were very, very interesting for me. I have two questions for our first guest, for Andrew. First of what I'm interested, if this kind of mathematic analysis is very sophisticated with very interesting and maybe heavy rules in mathematics with heavy formulas, could be applied not only for tonality, for a tonal system, but also for modal system, atonal system, and maybe for more recent tuning system or harmonic system. This is the first question. It's a little bit similar with Violeta asking. And the second one, because I'm quite interested in VUSA canons, which are related also with mathematics and with mathematic algorithms. I wonder if this VUSA canons can be also considered being related with fractal patterns, because are different from the regular canons or prolation canons.
On the first question, basically, if you can write, if there is a score and it's written in notes, or it can be converted to a score that's written simply in notes, then we can analyze it. Okay. It doesn't matter if it's a tonal or atonal, both can be analyzed. But, when you look at Carmen's scores, there are, in various places, there's notation that indicates a certain, shall I say, unorthodox use of instruments, for example, of the flute, of this bass flute. So this, I don't know how I'd have to think about how we would analyze this, because this can't really be written in terms of, it cannot be transcribed in terms of notes. At least I don't know how. On the second question, VUSA canons, if I correctly remember, but Violeta corrects me if I'm wrong, they don't really, they're not based on using different temporal scales, as far as I understand them. And in fact, I suggested to Violeta that she could write a VUSA canon that has such a structure, in which case these two principles would meet together. But as long as there is, fractals are a very special thing. People say, nature is fractal. Well, yes and no. It's mathematically, it's not exactly fractal. And people say trees are fractal. Well, yes and no, but they can't be really characterized by a single fractal number. So, to have a real fractal, whether it is in image or it is in music or in sculpture, is a very high order of specificity, mathematical specificity, so which I think is not generally present in VUSA canons. But I'm ready to be corrected by Violeta.
I shall correct you, but not here. We do not have enough time. But I shall correct you.
Thank you.
Anyway, now it's already 7:40. So, but if somebody would like to make a comment to say something, I'm happy. Yeah.
Perhaps because it is now so late, I have a very general question to both, and perhaps to the whole audience this evening. When I was very young, one of my first books was about symmetry in physics, and I was invited to Spain to a conference with all the still living in that time in the 80s Nobel Prize winners who founded the symmetric theory of modern physics. And then there was Eugen Wigner. Wigner, an amazing, highly cultivated person and a brilliant mathematician and the father of symmetry of modern physics. Now, anyway, he put a famous question, and with that question I want to conclude this meeting, because he asked why, very simple, why does mathematics so nicely fit nature? Very simple. Now my question is, why does mathematics fit so nicely music?
Right.
That's a very, very simple but very deep question, I think.
It's the
With a
beginning of a
Platonic
very
view, perhaps we have only an insight in an internal world of structures, and so we discover it as composer, as scientist, or are we constructing a projection? And with this projection, we explain music. Andrew has a projection of complexity research and explains music. Or are there some kind of perhaps eternal structures in the world, in music? That's a Platonic view, and we only discover it. I do not know. That's my question.
It's a wonderful question and the beginning of a very, very long story, a kind of roman fleuve. Thank you so much. And we are happy to meet you again in 2 weeks. And we wish you all the best. Thank you very much.
Thank you.
Thank you very much. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye-bye.
Graham Waterhouse to everyone. By how and whether canonic writing enhances the music. So, excuse me, Graham, I didn't see you before to desire to make a question. We can interrupt now. Graham, you are still there?
Yes, yes, I'm still.
Oh, please, excuse me.
Not
Can
at
you please
all.
tell us, yeah?
No, well, it's just the three examples that were given by Andrezej was almost like a revelation, especially in the Depré, where the meeting of rigorous contrapuntal laws seemed exactly to play into the enhanced listening and musical expression. And so often rigorously written theoretical music has a sort of dryness and academicism about it. But surely the point, if at all, of using rigorous laws or the laws of canon is to enhance somehow the message or the statement or the expression of the music. And just to say that I found that those three examples quoted completely did that. And then I thought, well, then that totally justifies the strictness of canon, i.e. meaning law in music. But where the law itself becomes the ultimate reason for the music, then somehow one misses the point. And by the way, there's interesting correspondence between Joachim and Brahms, who also wrote canons for each other. And I seem to remember asked the same question, whether the canonic aspect or the contrapuntal aspect enhances the expressivity of the music.
Can I say a few words in response to this?
Yeah, wonderful. Thank you. Please.
Yeah, thank you very much, Graham. That very lovely comment. First of all, I want to say that Brahms himself wrote a prolation canon, and we analyze it in one of our papers. So, and this kind of writing is, shall I say, rare, but it continues through the history of music literature. And Bach wrote quite a few other canons like this. He wrote regular canons and he wrote prolation canons. There is a, in the Well-Tempered Clavier, for example, in first book, number 8, there is at the end of the prelude, there is a prolation canon for 3 voices and 2 hands. Amazing piece. I also want to say that certain composers took a little bit of liberties. That is to say, when it was musically necessary to violate a little bit the rule, the mathematical rule that they were following, they did it without hesitation. And we have quite a few examples of this. So yes, the music integrity is supreme. It's more important than mathematical strictness. On the other hand, the mathematical strictness provides, as I wrote briefly, a certain perfection of form. So in the case of Josquin, for example, and Ockeghem, and several other Renaissance composers, for them to have a perfect mathematical form was an expression of their faith. It was an attempt to have a piece of music that would be absolutely perfect, and mathematics was considered a perfect form, right? And this Josquin example, but many others, are really truly amazing, because Josquin example, for example, is really exactly strict. And there is a piece by Delarue that's also like this, and many others. So your comments are very, very well taken. I appreciate them.
Thank you, Andres. And I see now Peter Hermann. Peter?
Yeah, I'm here.
Yeah, please.
Well, it's only, I don't know, more or less serious possible answer to the question about mathematics and nature and how it fits. That's Douglas Adams, who actually presented in a funny way why the puddle actually fits to everything, and why the puddle actually doesn't mention that it doesn't fit, but that it forces something to fit. It's at least one answer, one possible answer. Douglas Adams refers to environmental issues, and I think we should at least be careful in looking at any given fits or misfits, and consider as well what had been mentioned actually. If we force something into a certain pattern, you may have a look at this YouTube clip. It's 4 minutes, and it is at least entertaining, but I think it is as well something that may give us something to think about.
Thank you, Pedro. Thank you very much. I hope I didn't miss anything. I'm happy now to say again, thank you very much. See you in 2 weeks. We shall have Andrea Brini, Marius Ioanu Elia with us. Andrea Brini, he's a physician, also physician researcher, and Mario Ioanu Elia is a composer. Thank you very much, and see you in 2 weeks.